Okay, so far we've finished discussing z-test for population means involving one-sided greater than and one-sided less than alternative. Now the third variation is the third type of hypothesis. This is two-sided not equal to. And from the start of the chapter, this is one of our examples. So this is the Valentine's Day case. So the null and the alternative were already determined. The mean for the null hypothesis, the mean is equal to 330. And for the alternative, the average is not equal to 330. So remember, we want to know if the average number of boxes sold for all the stores is 330 or not. So in this case, we will use two-sided. Now, again, the second step is to identify the values for alpha. Here, we'll again use the 4. So we have 10%, 5%, 1%, and 0.1%. Now, in step 3, we will identify the test. Here, we are making interpretations about a mean. The sampling distribution of the sample mean is approximately normal. So even if we don't know the distribution of the sales for all the stores, the sample size was 100. And furthermore, the population standard dev is known. So based on these three information, we can use the z-test for means. Now again, there are two methods in testing hypotheses. For the first one, that's critical value method. Again, we need to identify critical values and test if the test statistic will be inside the rejection area. Now, for critical value method for two-sided, as mentioned before, there should be two critical values for every value of alpha. So if this is your z-curve, again, for every value of alpha, there should be two critical values. So the total area of the rejection area should be equal to alpha. So if that should be divided into 2, then two sides should be alpha over 2. So for the first value of alpha, which is 10%, the first critical value will be the critical value with 5% width left, and the other one is the critical value or the z-score with 5% width right. So we write that as negative z sub 0.05 and positive z sub 0.05. And if you search for these critical values in the table, you will get negative 1.645 and 1.645. So these are the critical values for an alpha of 10%, which means that if the test statistic is less than negative 1.645 or greater than 1.645, then we will reject the null hypothesis at 10%. Now we do that again for the three other values for alpha. So for 5%, that's 2.5% each for the two sides. So this is negative z sub 0.025 and positive z sub 0.025. And if you search for these in the table, we will get negative 1.96 and 1.96. For an alpha of 1%, that's negative z sub 0.005 and positive z sub 0.005. And looking for these z-scores, we will get negative 2.575 and 2.575. Finally, for an alpha of 0.1%, again, divide that into 2. So this should be negative z sub 0.0005 and positive z sub 0.0005. So looking for these in the table, so that's 0.0005. So we will get the z-score, which is this. Okay, that's negative 3.29. So that's negative 3.29 for the left side, and then for the other side, that's 3.29. Okay, so these are the critical values for this test. So again, if the test statistic falls inside the rejection area, then reject the null hypothesis. Now, the test statistic is computed using the same formula. That's x bar minus mu naught over sigma divided by the square root of n. So again, in this case, we will use the shorter formula for the denominator because we don't know capital N, and for this case, it's safe to assume that it's large enough. So when you divide that by n, by small letter n, it's still at least 20. So in the problem, the sample mean provided was, the sample mean was 326. Mu naught is 330. Sigma is also given, that's 40. And divide that by the square root of n. So computing for this test statistic, we will get exactly -1. So once you have this, just locate that with respect to the critical value. So -1 is somewhere here. Okay? So this is the location of the test statistic. So if you look closely, this test statistic is not inside the rejection area for 10%. So it's not to the left of -1.645 nor to the right of 1.645. So for 10%, so if we were to make the decisions for the four values of alpha, for 10%, okay, we do not reject the null hypothesis. Now, if you compare the test statistic again to the rejection areas for the three other values for alpha, the test statistic is still not inside. Therefore, for all the four values, so 5%, 1%, and 0.1%, the decision will still be do not reject the null hypothesis. So in this case, since our decisions for all the four values of alpha are do not reject the null hypothesis, then we can start the interpretation with we don't have enough evidence, or we have insufficient evidence. So that can be the start of your interpretation. So in this case, the complete interpretation can be we don't have enough evidence, or there is insufficient evidence to support the claim that the average number of boxes sold for all the stores of the company is not 330 boxes. Okay, although the sample mean 326 is not equal to 330, this is not enough for us to conclude that the average for all is not equal to 330. So that's how we perform the critical value method. Now, under p-value method, again, the rejection rule is always the same. It doesn't change. We only reject the null hypothesis if the p-value is less than alpha. So in this case, the computed test statistic is -1. So the p-value should be based on this test statistic. So if you try to locate -1 along the curve, this is the test statistic. Now, the p-value, again, is an area. But in this case, remember, this is two-sided. So the area should also be two-sided. So if you get the area to the left of -1, that's only 1/2 of the p-value. So for us to get the total p-value, so you can just multiply this by 2. Or, in theory, that adds the area to the right of +1. Okay? So you can just add the area to the left of -1 to the area to the right of 1, or just get this area and then multiply that by 2. So if we use the table to look for the area to the left of -1, according to the table, that's 0.1587. So this area is 0.1587. This one should also be 0.1587. So to get the total p-value, just add the two or multiply the area of one side, and we will get the total p-value, which is 0.3174. So the p-value is 31.74. Now, if you compare this to the four values of alpha, clearly the p-value is greater than all the four values of alpha. Therefore, similar to the results of the critical value method, we do not reject the null hypothesis for all the four values of alpha. So the interpretation will also be the same. You don't have enough evidence to support the claim that the average number of boxes sold for all the stores of the company is not 330 boxes. So that's the p-value method for two-sided not equal to test. So we're now done discussing the different variations for the z-test for means. Now we can proceed to the second test, which is the t-test. So similar to confidence intervals, t-tests can only be performed if you are estimating the mean, the sampling distribution of the sample mean is normal, and the population standard dev is unknown. So it's again very similar to confidence intervals. So instead of z, we now use t. So the formula for the test statistic as shown in the handout is also different. Instead of sigma, the t-score will now be x bar minus mu naught over sigma divided by the square root of n. Instead of sigma, that should now be s. Now, in the example in the handout, the problem is for us to determine if the population mean is greater than 10. So if we first construct the null and the alternative hypotheses, so again, the problem specifically states that we wish to determine if the population mean is greater than 10. So that should be your alternative hypothesis, that's mu greater than 10. And for the null hypothesis, that's either mu less than or equal to 10 or mu is equal to 10. Now, step 2 again, let's use all the 4 values of alpha. And in step 3, we will identify the test. So again here, we are estimating the average of a population. The problem specify that the distribution of all the values of x is normal. Hence, even if the sample size is only 16, the sampling distribution of the sample mean is exactly normal. So that's according to the central limit theorem. Now, sigma is unknown. The problem does not provide us with the population standard dev. So based on these 3 information, we can say that the correct test should be the t-test for the population mean instead of the z-test. Now, again, we have 2 ways to perform the t-test. First is through critical value method. So the critical value method for t-test is very similar to the critical value method for z-tests. The only difference here is that instead of using the z-table, we will now use the t-table. So this is one-sided greater than. So similar to z-test, the critical value should come from the right. So if this is your z-curve, then we have one critical value for every value of alpha. We have 1 for 10%, so we write that as 10 sub 0.1. We also have 1 for 5%, t sub 0.05. We also have t sub 0.01 and t sub 0.001. Now we can determine these t-scores from the t-table. So degrees of freedom for this problem is 16 minus 1. So we just have to look for the t-score under DF, for DF15. So for t sub 0.1, that should be 1.341. For 5%, that's t sub 0.05 up to 15, that's 1.753. For 1%, that's 2.602. And for 0.1%, that should be 3.733. So the rejection rule is the same. If the test statistic is inside the rejection area for that value of alpha, then reject the null hypothesis. Now, computing for the test statistic, again, the formula is now slightly different. So instead of z, this is now t sub stat. And the formula is now x bar minus mu naught over s divided by the square root of n. So again, we don't have the finite population correction factor because here, the population is assumed to be infinite. Now, the sample mean given in the problem was 13.5. Mu naught is the one at the hypothesis, that's 10. The sample standard dev is 6, and the sample size is 16. So when we compute for this test statistic, so again, that's 13.5 minus 10 over 6 divided by the square root of 16. So computing for this test statistic gives us 2.33. That will be the test statistic. And then to make the decisions, we check if that test statistic is inside the rejection area. So 2.33 is somewhere here. That's T sub stat equal to 2.33. That's inside the rejection area for 10% and 5%, but not for 1 and 0.1. So in that case, if we were to make the decisions for those values of alpha, again, for 10% and for 5%, we will reject the null hypothesis. And for 1% and 0.1%, we do not reject the null hypothesis. Okay? So since we were able to reject the null hypothesis up to 5%, then in terms of the weight of evidence, we can say that we have strong evidence. Okay? So here again, just continue with the interpretation using the actual variable. The problem does not provide an actual variable, so we can just say population mean. So again, that's we have strong evidence to support the claim that the population mean is greater than 10. So that's critical value method. Now for the other method called the p-value method, again, the rejection rule is the same. We only reject the null hypothesis if the p-value is less than alpha. So the test statistic that was computed earlier was 2.33. Now we have to look for the p-value. So if this is your t curve, 2.33 is positive, so that's to the right of the average. Now again, this is one-sided greater than, so this must be the p-value. However, the problem here is that the t-table is limited, so it cannot provide us exact areas for all t-scores. So in this case, under degrees of freedom 15, we have to search for 2.33, and that's not here. Okay? So 2.33 is in between 2.131 and 2.602. So if we were to show that in the graph, then this must be 2.131, and then somewhere here should be 2.602. Now, according to the table, the total area to the right of 2.131, so from this point to the rightmost, okay, that total area is 2.5%. Okay? Now, also according to the table, from 2.602 up to the rightmost, this total area is 1%. So if 2.33 is in between 2.131 and 2.602, then this total area from 2.33 to the rightmost should be any area or any probability in between 1% and 2.5%. So it can't be equal to 1% because the test statistic is not 2.602. So it has to be something bigger than 1%. And at the same time, the area should also be less than 2.5% because the test statistic is different from 2.131. So the total area, or in this case, the p-value, is somewhere between 1% and 2.5%. So we use open and close parentheses to signify that these endpoints are not included. These are not possible values for the p-value. Now, even if the p-value is not exact, this is still enough for us to make conclusions or to make decisions. Because again, we don't know the exact value. It should be somewhere between the two. But even if we don't know the value, we can say that whatever that value is, it's less than 10%, right? Because the entire value is less than 10%. So if it's less than 10%, then we can reject the null hypothesis at 10%. Now for 5%, the total area again is less than 5%. So the area can be anything inside this. And again, it's only between 1 to 2.5%. So it must be less than 5% as well. So in that case, we also reject the null hypothesis at 5%. But for 1%, again, the interval clearly states that the area should be more than 1%. So in that case, we cannot reject the null hypothesis at 1% and even for 0.1%. So we will have the same set of decisions and even the interpretation. So we have strong evidence to support the claim that the average of the population is greater than 10. So that's the t-test for one-sided greater than alternative. Now, if you try another kind of problem that uses the t-test but it has a one-sided less than alternative, then the things that will change first will be the critical value. So the critical values will now come from the left, and in that case, the critical values are negative. So the rejection area will be the area to the left of the test statistic. Now, the table does not give us negative t-scores, but remember, the t-table is symmetrical, so you can just convert these to the negative signs. So that's how we get the critical values for one-sided less than. Now, for p-value method, it's the same practice. So the total area to the left will now be the p-value. So in that case, you can again come up with an interval for the possible value of the p-value, and that should be enough to make decisions. Okay? Now for two-sided, okay, similar to the z-test, critical values will come from both sides. So for every value of alpha, there should be two critical values. So divide the alpha again into 2, but again, in this case, you have to get the t-scores from the t-table. And for the p-value method, one area to the right or to the left will be just 1/2 of the total p-value. So if this is for a two-sided t-test, okay, this is only 1/2. And to get the total p-value, we multiply the entire interval by 2. So in this case, if this was the area of one side, and this is a two-sided t-test, the total p-value should be between 2% and 5%. So in that case, you now have the interval, and you can now make interpretations again if it's less than the value of alpha. Now for the last kind of test, that's the z-test for the population proportion. So again, similar to confidence intervals, this is only used if you are making inferences about the population proportion. Let's say proportion of those who are females, or proportion of those who are males, or proportion of those who are in favor of a tax increase, or any other proportion. So again, we are now dealing with qualitative variables. So it's also a z-test, so we also use the z-table. And again, z-test can only be performed if the sampling distribution of the sample proportion is normal. And finally, here we don't care about the value for sigma, because remember, there is no sigma in the first place, because this is a proportion, this involves a qualitative variable, so it doesn't have a standard deviation. So the entire process is the same with the z-test for means. The only difference here is the formula for the test statistics. I'll show that later. So in the example in the handout, we wish to test the pair of hypotheses that were given. So the null and the alternative were given in the handout. For the null, that's rho is greater than or equal to 0.8. And for alternative, that's rho is less than 0.8. So again, we can test this using the 4 values of alpha. And here, in step 3, we will identify the correct test. So first, we are making inferences about the population proportion. Now, we want to know if the sampling distribution of the sample proportion is normal. And to check that, we will use these two equations, again, consistent with the central limit theorem. So n times rho in this problem, so the sample size is 400, rho naught is 0.8, so that's 400 times 0.8 or 320. For the next equation, that's 400 times 0.2, that's 80. Both are at least 5. So we can say that the sampling distribution of the sample proportion is approximately normal. Okay? So based on these two, we can say that the correct test should be the z-test for the population proportion. Now, under critical value method, again, we will set the rejection areas. And again, that is dependent on the type of the hypothesis. Here, this is one-sided less than, so the rejection areas or the critical values should be from the left. So if this was the z curve, okay, again, this should be negative z sub 0.1, negative z sub 0.05, negative z sub 0.01, and one more, that's negative z sub 0.001. Now, we've already determined these z-scores before, and these are just negative 1.28, negative 1.645, negative 2.33, and negative 3.09. So, the rejection rule is the same. If the test statistic is less than the critical value, then for that value of alpha, reject the null hypothesis. Now, the test statistic now uses a new formula. This is a proportion, so we will use the formula from chapter 7. That's p hat minus rho naught over the square root of rho naught times 1 minus rho naught over n. Okay? So, p hat from the problem is 0.74. Rho naught is the one at the hypothesis, that's 0.8. And then divide this by the square root of 0.8 times 0.2 over the sample size of 400. So when we compute for this test statistic, so again, that's 0.74 minus 0.8 over the square root of 0.8 times 0.2 over 400, we will get the test statistic of negative 3. That's exactly negative 3. Okay? And then locate that again with respect to the critical values. Now, test statistic is somewhere here. So, z sub stat is negative 3. Now, since we now have the test statistic and the critical values, we can now make the decisions. So, in step 6, again, we make decisions for all the 4 values of alpha. You have 0.1, 0.05, 0.01, and 0.001. The test statistic is inside the rejection area for 10%. It's also inside the rejection area for 5% and even 1%. So it's not inside the rejection area only for 0.1%, which means that your decisions for the first 3 values of alpha are the same, and that's reject the null hypothesis. But for the last one, we do not reject the null hypothesis. So here again, we have rejected the null hypothesis up to 1%. So in terms of the weight of evidence, we can see that we have very strong evidence. So if you complete the interpretation, we use the exact weight of evidence and the variable. The handout does not mention what proportion this refers to, so we can just say that we have very strong evidence to support the claim that the population proportion is less than 0.8 or less than 80%. So that's critical value method. Now, under p-value method, again, rejection rule is the same. We reject the null hypothesis if the p-value is less than alpha. So the test statistic that was computed earlier was negative 3. So if we compute for the p-value, again, this is one-sided less than. So if this is the test statistic, negative 3, then the p-value should be the area to its left. So this should be the total p-value. And if you look for that p-value in the table, we will get 0.00135. So comparing this to the 4 values of alpha, it's less than 0.1, 0.05, and 0.01, but it's slightly bigger than 0.001. So again, we will have the same set of decisions. We will reject the null hypothesis for 10, 5, and 1%, but for 0.1%, we do not reject the null hypothesis. So the interpretation is also the same. We have very strong evidence to support the claim that the population proportion is less than 80%. So that's p-value method for z-test for proportions, which is one-sided. Okay, and specifically that's one-sided less than. So if you have another problem that's one-sided greater than, so again the changes here should be that the critical value should be positive, should come from the right, and the p-value is the area to the right of the test statistic. If you have z-test for proportions, which is two-sided, so again critical values will come from both sides, and p-value should be two areas, so the area to the left or to the right of the test statistic, and then multiply that by 2. So that's the z-test for population proportions. So again, it's very similar to the z-test for means. The only change here is the formula for the test statistic.